Good morning, grade 11s. Now we're going to have a look at ionic bonding. Now, as you know, ionic bonding is between a metal and a non-metal. For our purposes, we don't have to look at the difference in electronegativity. As soon as we have a metal bonding with a non-metal, we take it as an ionic bond. Now, in an ionic bond, we deal with a transfer of electrons, and the electrons are transferred from the metal to the non-metal. And it's because the metals have a lower electronegativity than the non-metals. And so the non-metal has a much higher electronegativity and then actually takes the electron from the metal. Now, I'd like to start off by looking at what we have to know about ionic bonding from the SAGS document. So you need to know that you must define an ionic bond as a transfer of electrons, and as I said, it's from the metal to the non-metal, and a subsequent electrostatic attraction. I'm going to discuss that in a moment. You have to know that ionic bonding is generally between metals and non-metals. And next slideshow will be metallic bonding, and you need to define a metallic bond as being between a positive kernel and a sea of delocalized electrons. But for now, we're going to focus on ionic bonding. So firstly, I'm going to look at NaCl. So NaCl is plain old table salt. Now, if we look at sodium, it's in group 1 of the periodic table, so it has 1 valence electron. And then chlorine is in group 7, it's a halogen, and it has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. And we can see that there are 3 lone pairs. Those are the electrons that have partners, and then this electron here is an unpaired electron, and so it needs a partner to be stable. So what happens is the electron from the sodium transfers here to the chlorine. So if we have a look, because the sodium has lost its valence electron, it becomes positively charged. It has fully lost the electron. There's no sharing of electrons whatsoever. Then the chlorine has gained an electron. It's gained an electron. So the chlorine becomes negatively charged. So what happens is we have a positively charged ion, that's called a cation, and we have a negatively charged ion, and that is called the anion. And what happens is the positively charged ion and the negatively charged ion, they attract one another because positives and negatives attract. So they stay together, and that attraction is an electrostatic attraction, and that is what is known as the ionic bond. Now here, I've just shown you between 1 sodium and 1 chlorine, but there's actually millions that are busy bonding and losing electrons. And so what happens is we do not get a molecule when we look at an ionic bond. A molecule is a result of an equal sharing or an unequal sharing of electrons, but it's about the sharing of electrons. So there has to be a covalent bond or a polar covalent bond to make a molecule. Here we get the ions, and the ions are attracted together by this electrostatic attraction, which is the ionic bond, and it forms an ionic lattice. So it's all of these ions, the anions and the cations, they're attracted to one another and they stay together in this giant ionic lattice. You don't have to know how to draw the ionic lattice. It's just to show you what it looks like. The next example we're going to have a look at is a little bit more complicated. It's aluminium oxide. So we know that aluminium is in group 3 of the periodic table, so it has a valency of 3. Oxygen is in group 6 of the periodic table, so it has a valency of 2. And so I've taken the 2 down from the top of the oxygen to be there by the aluminium, and I've taken the 3 down from the aluminium there by the oxygen. And so we get Al2O3. So that means I've got 2 aluminiums involved in this bond, and I've got 3 oxygens involved in the bond. Now, what type of bond is it? Well, we have aluminium, which is a metal, and we have oxygen, that is a non-metal. So as soon as we have a metal and a non-metal going together, we know that it's going to be an ionic bond. So I've shown that I've got 2 aluminiums over here, and I've got 3 oxygens. Now, aluminium is in group 3 of the periodic table. So there's 1, 2, 3 valence electrons, and the other aluminium is the same. It has 3 valence electrons. Each of the oxygens is in group 6 of the periodic table. So it's 1, 2, 3, 4, 5, 6. Now we can see that oxygen has 2 lone pairs and it has 2 unpaired electrons. Now the unpaired electrons are going to need to get partners in order to become more stable. And that completes the octet rule, because then it will have 8 electrons in its outermost energy level, which makes it more stable. Now, aluminium is rather going to lose these 3 valence electrons. So what happens if we've got 3 oxygens? Each of these oxygens needs 2 electrons. So this one, this valence electron, will go there to that oxygen, so that aluminium's lost 1. There, it will go there to that oxygen. Now this aluminium has 1 left, and so that one will go partner up there with that oxygen. Then from this aluminium, the valence electron will go there to that oxygen. This one will go there, and this one will go there. So now each of these aluminiums has lost 3 electrons. So if it's lost 3 electrons, it's going to get a 3+ charge. Now each of the oxygens has gained 2 electrons each. Remember, if we gain electrons, then we form an anion, which is a negatively charged ion, and each of these oxygens has gained 2 electrons. And so it gets a charge of 2-. So if we have a look over here, I'm representing the ionic bond over here. I'm summarizing. So we had 2 aluminiums. Both of the aluminiums lost 3 electrons, and that's why we've got 2 aluminiums, and they've both got a 3+ charge. Then we had 3 oxygens, represented there by that 3. I put it in square brackets, and then each of the oxygens, each of the 3 oxygens has gained 2 electrons, so they have a charge of 2-. You mustn't forget to put the charges over there. And because we have positive charge and we have a negative charge, they attract one another, and that electrostatic attraction is called the ionic bond. And again, we have millions involved in the bond, and it forms an ionic lattice. Remember, you don't have to know how to draw the ionic lattice. I'm just showing you what it looks like. Then finally, I want to look at some properties of ionic compounds, but I just want to look at 3 examples. So for example, we have table salt, we have magnesium carbonate. So when we have a polyatomic ion like the carbonate, and that has a negative charge, and if it is bonding with a metal, then we get an ionic bond. Now magnesium carbonate is an example of an ionic compound, and that can be used to boost your immune system. And then we have potassium permanganate, and that can be used as an antifungal if we're looking at its medicinal value. So now if we look at the properties of ionic compounds, now if you see what they look like, they look brittle. So one of the properties is that it's brittle. Another property is that it has a very high melting point, and we'll be looking a lot at this in the next section when we're dealing with solids and substances and looking at their boiling points and melting points. But if it has a high melting point, it's telling us that it's got a very strong bond, and ionic bonds are very strong bonds. Another property is that it does not conduct electricity in the solid state. If you think of the ionic lattice, those cations and anions, the positively charged ions and the negatively charged ions are packed very closely together in a solid, and the ions can't move around. And so we need the ions to be able to move in order to conduct electricity. And because there's no movement in the solid state, it can't conduct electricity. If we melt it into a liquid, and it has a very high melting point, so we have to use very high heat and heat it to a very high temperature. But if we do get it to melt, that is what is called the molten state, when we've melted something into a liquid. Then because in a liquid form the ions are further apart, they're free to move, then it will conduct electricity. And another property is if you dissolve the solid in water and you make a solution, then the ions are also free to move and they will conduct electricity as well. So high melting point, because very strong ionic bonds, so you need to add a lot of heat and energy in order to break it. It does not conduct electricity in the solid state because the ions are not free to move. But if we melt it and make it into a liquid, then the ions are free to move and it can conduct electricity. And then finally, if we dissolve it in water, we make a solution of the ionic compound, then it will conduct electricity. As I explained, ionic bonds have very high melting points, and that's because the ionic bond is very strong. And if we have a look at NaCl, it has a boiling point of 801 degrees Celsius. Remember, the boiling point of water is 100 degrees Celsius, so NaCl is 8 times that. And then if we have a look at the aluminium oxide, it's 2072 degrees Celsius. And so now why do you think the NaCl, even though it has a high melting point, why is it lower than the aluminium oxide? And so remember what I told you, the strength of the melting point is dependent on the strength of the ionic bond. Now, when we looked at NaCl, there was only a transfer of 1 electron. And so the cation just has a +1 charge, and the anion has a -1 charge. So the charges are much weaker than in aluminium oxide. So the aluminium, because of the transfer of more electrons than the 1 electron, each aluminium transferred 3 electrons. So the cation here has a 3+ charge, and each of the oxygens has a 2- charge. And so because the charges are much bigger, it makes for a stronger ionic bond, and we need to add a lot more heat in order to break it. And so even though both of them are high melting points, because there's more of a transfer of electrons in aluminium oxide and we result in higher charges, it makes the ionic bond much stronger.